Good day, my name is Maria Zhikovska and welcome to today's presentation on integrated reaction of osmium carbon complexes with bromine and hydrogen peroxide. These reactions provide a valuable insights into reactivity profiles and potential application of these compounds in organometallic chemistry. Osmium carbon complexes have garnered significant interest due to their unique structures and diverse reactivity patterns. Understanding their reactions with oxidizing agents like bromine and hydrogen peroxide is crucial for elucidating their mechanisms and exploring their synthetic utility. The molecule is organometallic complex featuring osmium at its center. The arrangement of ligand around the osmium center results in octahedral geometry. The chloride ligands, vinyl carbene ligands, and triphenyl phosphine ligands occupy positions around the osmium atom, defining the overall structure of the complex. The triple bond between osmium and carbon in the carbene ligand is crucial for the reactivity of these complexes. This bond is characterized by strong sigma and pi interactions, contributing to the stability of the complex. The bonding in the molecule involves the combination of covalent and coordinative covalent bonds. Covalent bonds form from between the osmium atom and the ligands, with the sharing of electrons pairs between the metal and the ligand atoms. Coordinate covalent bonds are formed when the electrons pairs in the ligand are donated to the empty orbitals of osmium atom, resulting in the coordination of the ligands to the metal center. The octahedral osmium carbene complex has 3 chloride ligands bound. As the overall complex is neutral charge, the osmium center mass proposes the oxidation state of +3. Electron counting of osmium complex also reveals it follows the 18 electron rule, wherein the carbene ligand contributes 3 electrons to the overall number of valence electrons. The 18 electron rule is consistent with an octahedral coordination of the other osmium-based complexes. You can see ionic and covalent method of electron counting. The bromination of osmium complex occurs through a number of dissociative mechanisms. The triphenyl phosphine is a sterically expansive ligand and will likely dissociate, leaving a vacant site for bromide ligands to fill. The 2 chloride ligands trans to one another are replaced through either an associative or dissociative mechanisms to form the 2 trans-bromide ligands. The water will replace the labile chloride ligand to form the most stable isomer of the complex, with water trans to the vinyl carbene group. To form this complex, the reaction requires a great excess of bromine and water and had a reaction time of 15 hours with multiple sites of product observed. As such, there is clearly a variety of competing reactions. In principle, complex 10 could also have either isomers, for example, complex 10A, in which H2O is trans to PPH3, and complex 10B, in which H2O is trans to bromide ligand. The complex 10 is stable due to its favorable bond lengths and angles, which minimize the steric hindrance and electrophilic repulsion, while 10B is less favorable compared to 10 or 10A because of the presence of H2O trans to a bromide ligand that likely introduces strain or electron destabilization. The reaction with hydrogen peroxide and hydrochloric acid yields a product wherein the beta carbon will undergo chlorination. Due to the presence of the hydrogen peroxide and the lack of any reaction of the beta carbon with bromide suggests that the mechanism requires a strong oxidating agent. As the peroxide is attached, it will form an epoxide. The chlorine will then attack the less sterically hindered site. Additionally, peroxide molecule will react with the oxygen to form O2 and water, as well as remove the hydrogen bond to the beta carbon to form H2 gas. The formation of these gases acts as an entropic-driven force behind the reaction. This is evident in the short reaction time of 1 hour at the room temperature. Analytical methods such as NMR spectrometry, mass spectrometry, and X-ray crystallography play crucial roles in studying the reactions and characterizing the products. These techniques offer valuable information about the identity, structure, and the purity of the complexes before and after the reaction, aiding in the mechanism elucidation. In conclusion, the reactions of osmium carbene complexes with bromine and hydrogen peroxide showcase a rich chemistry and diverse reactivity of these compounds. Understanding the mechanism and factors influencing reactivity is crucial for rational design of new catalysis and materials in tailored properties with implications for catalysis and material science. Further studies could focus on exploring the reactivity of osmium carbene complexes with other oxidating agents and functional groups, expanding the scope of the synthetic applications. Investigation of the catalytic potential of these complexes in oxidation reactions and other transformation could lead to the development of new catalytic systems with enhanced activity and selectivity.